Hello there, in this video we're looking at parabolic motion in an electric field. So here I've got my parallel plates arranged here like so, positively and negatively charged, and there'll be an electric field inside this space that's uniform in magnitude and direction. And that means that this particle will experience an acceleration that's uniform in magnitude and direction as well. And we're going to describe the motion of this particle and what equations we need to use and things like that. Now, to start off with, regardless of the particle's motion, we already know some information. First off, perpendicular to the field, or in this case, horizontally, because here the field will be going like this, upwards and downwards. So here the velocity component that will be perpendicular to the field will be left and right, which is the horizontal component of the velocity in this case. That's not affected by the acceleration from the field at all. So the acceleration horizontally perpendicular to the field in this case will be 0. And that leads us to equations that are going to help us horizontally here. And that is that the speed horizontally, so I'll add a little subscript h to make sure we remind ourselves we're talking about just the horizontal velocity there, is going to be the displacement over time. Speed equals distance over time, your basic equation like that. And a lot of time we can use it to calculate how far it's going to travel horizontally. And that will be by multiplying the horizontal velocity by the time, like this one here. So what you'll sometimes get is questions where you'll have a particle and it's got a velocity like this, perpendicular to the field, and immediately you should notice that that is an entirely horizontal velocity, and they might just give you VH by itself to begin with, like that. That's not a H, come on H. And they also might give you how far along the plates are. So they might give you the distance from here all the way down to the end. They might give you that displacement there. And that is a horizontal displacement as well. So you can use this horizontally with this horizontally in combination, and we can calculate, say, the time. We can rearrange that for the time, and we can figure out how long it's in the field for, which can be useful information. So perpendicular to the field, we always have acceleration as 0, and we use your basic speed is distance over time kind of formulas when working perpendicular to the field. In this case, yes, that is horizontal, but just keep in mind that this entire situation can be rotated 90 degrees, and it becomes the vertical component that is a constant. So we always need to remember perpendicular to the field. So if we're working perpendicular to the field, A is going to be 0. We get 0 acceleration perpendicular to the field, and our velocity is going to be constant. So I'll just add that in there as well. So parallel to the field, the velocity that's in the up and down direction here, that will change. That's the one that experiences the acceleration. How much acceleration? Well, it's going to experience an acceleration of QE over m. So we just need to know the electric field strength, what charge we're dealing with, and what mass does it have, and that will give us what the acceleration is there. Something to take note of is the direction of the acceleration. That's going to depend on whether the particle is a positive or a negative charge. So in this example here, if this was a positive charge, we would expect it to accelerate in the direction of the field lines, which would go from positive to negative. So we would expect the acceleration there to be downwards if it was a positive charge. Come on, acceleration. There we go. If it was positive, acceleration will be downwards, and if it was a negative charge, it will be accelerating upwards towards the positive plate. Okay? Yeah, so if it was a negative charge there, the acceleration will be upwards towards the positive plate. And that acceleration would not change throughout its entire motion. It would always still be pointing the same way. Notice that it's at right angles to this component of the velocity, which wouldn't change because it's completely perpendicular to the acceleration. That's why that acceleration in the other direction is 0, and that component of the velocity will remain constant. If we're working with an acceleration in that direction, that means to solve problems we have to use the equations of motion that involve acceleration, because there is an acceleration. And all the equations of motion have acceleration in them as a variable, so that's why we use them. Notice that this one here does not have acceleration because acceleration is 0 in that direction, so we just use speed as distance over time. Acceleration doesn't matter. But as long as we have acceleration, we end up using the 3 equations of motion. There's our 3 equations of motion there, and that's what we'll use in the vertical direction. What we'll do next is we're going to see how we can use these equations in 2 different examples of a possible motion that we might look at that involves some kind of parabolic path, and see which ones are useful. The first one we'll consider is kind of this problem here. We'll keep the charges negative, so the acceleration is going upwards all the time, and it starts off with a horizontal velocity that's going to be constant the entire time. So it's going to gradually move through the plates, but it's also going to be accelerating upwards. So we'll get a curved path, and it's going to exit somewhere around here. So I've just highlighted in the original path that we'd expect the particle to go if the plates were turned off, and it could just continue at a constant velocity. So we can compare its deviation to that. So I'm going to pick a color to put the particle's path in, the new path, and we'll have a go. So with the added acceleration, it's causing this deviation to the path that we can see here. And what we can do, and a question that you might get asked is about how does it deviate from its path originally, and we call that its deflection. One of the things you might be asked to do is to calculate how much this deflection actually is. Because that deflection is in the direction parallel to the plates, it'll be a vertical deflection here. So we're going to work vertically with an acceleration. We have to use one of the equations of motion because we're acting vertically. We must use one of these equations. We want to choose the right one. First off, we'll consider some information in this situation. We'll assume that we can find the acceleration pretty easily. If we look at the beginning here, to begin with, this particle has no vertical velocity. It's all horizontal. So already we know that the initial component of its velocity is just 0. So we can use that information. And in this case, it's pretty useful when we look at this equation here, because our displacement is going to be our initial velocity times by the time. Our initial velocity is just 0, so that term completely disappears, and we're left with 1/2 times by the acceleration, which is over here, multiplied by the time squared. We just need to know how long does it take for it to reach there, and then we can use that to calculate what deflection do we get. And there might be different ways that we can do that, but one way in particular is to work with the horizontal component, this component here. We can use this in conjunction with how far does it go to work out the time horizontally. And the time is universal, it's going to be the same time everywhere, so we can use that time over here and calculate the deflection that way. So this equation is really nice for doing that. It's really good for calculating how far up or down does it go compared to its original path. And that second equation is really useful for doing that. In this kind of problem, the other two aren't as useful. The top one might be used to say find how fast is it going at the end, because we can substitute in the time and the initial velocity to do that, but by far the calculating deflection is a bit more useful there. In this next problem we'll look at, we'll send it off at a velocity, so we'll get a different kind of path. If we think about here, we're still using a negative charge. It'll start off, hold on, just switching colors. I want green. Give me green. So we'll start off by going this way. Because it's a negative charge and the positive plate is up here, it should be accelerating towards the top plate just as before. So we'll find that it follows a curved path that reaches a maximum, or it might even strike the bottom plate, but we're going to make it curve and then start traveling back this way. So the kind of path that we'll see might look something like this. And that loaded in properly that time. And there we go. Once again, I'm putting in a reference line there for us to compare to. And we can do things like calculate like how far does it get displaced from its original position, like that. Or how long does it take to reach that position, and other things like that. But in this problem, what we'll probably need to do first off is realize that this starting component, this starting velocity isn't split up into components yet. It's just a total velocity. We can split it up into two components that both add together like so. There's a kind of mini vector diagram there to make that total velocity. To find those two components, because we'll need to work with them, we use two equations to do that. For the horizontal component, we can always find it, no matter when we're looking at, by doing v times by cosine of the angle. And the vertical component, we can do it by using v times by sine of the angle. There we go. So we can use those two formulas, and that will give us what VH is, which in this case is going horizontally there, and V for the vertical direction, which is there. Something to note about this VV vector here, this vertical direction one, that actually tells us what V0 is going to be originally. So V0 is kind of intrinsically related to this equation here, because if we use it to begin with, and a lot of the time we do, it tells us what the vertical velocity is to begin with, because that's the component that's going to change in this, at least in this case here. So if we're working with this point here, at this point where it reaches like a vertex, at that point the vertical velocity is going to be 0 as it's changing direction. So as we work vertically, we can use the fact that v equals 0 in these equations here, not the horizontal velocity, mind you, just the vertical velocity. So the horizontal velocity is still going to be constant. It's going to be this the entire time. It will never change. It's the vertical velocity that's 0 at this point. So over here in the equations of motion, we can substitute v equals 0 here and use that to calculate a few things. We can use this last equation and have v equals 0, combine that with our vertical velocity, which we should already calculate, to find out the displacement, if we know the acceleration, by using this formula here. So this last one here, really useful for calculating a displacement to some kind of max or min point in the path of the charged particle. So this value here, to calculate it straight away, without needing to do anything else, we can use this equation here, and if we substitute the fact that v is going to be 0, we're going to end up using this equation here to do that. Notice that you might have noticed that we can find the time it takes to reach that point by using the first equation here, because then v equals 0 at that point, and we can find the initial velocity, we can find the acceleration. Initial velocity was from here, acceleration from here, so we can use this equation at the top to do that. So there we go, so that equation here, useful for finding the time it takes to reach that point, and you'd end up rearranging it to this equation here if you use v equals 0 and then start rearranging the equation. And there we go. There's more we can talk about in regards to doing problems here, but the reality is you need to do lots and lots of them in practice to see the full gamut, because they can take different forms there. Thanks for watching, and I'll see you next time.